Okay, so one nice example that I can give you of Weierstrass theorem is basically definition of matrix norms. So that's a very interesting thing. You will you will need it a lot if you do things like singular value decomposition or anything machine learning compression whatever. Many examples of this where matrix norms are used. So let me define uh, uh, a norm matrix norm of a so what we have got here, let's say that let A be the set of all m cross n matrices. So you fix m and n. No, A, B, C, D. Those are the kind of consider all m cross n matrices. Oh God, sorry. Consider the set of m cross n matrices. So let A be a matrix in which is a real m cross n matrix. Then we can define a norm function which is from the space of m cross n matrices. So norms are always non-negative, so R plus, such that it should satisfy those three inequalities. The norm of A should be greater than or equal to 0. It is always negative, and 0 if and only if A is 0. Other A is a 0 means A is a 0 matrix, a m cross n 0 matrix. 2. If there is a function called norm function, then if you apply to it to the sum of two m cross n matrices A and B, then the length or the norm of them should be less than or equal to individual lengths of A and B. And 3, if I scale A matrix by a scalar alpha, then the norm should also be scaled by the modulus of alpha. This is your triangular inequality, this is the scaling property, and this is the non-zero property. So these are the three key properties that if you can invent a function which meets these properties, then you can actually define a distance kind of a function or a norm function on also on the m cross n matrices. So based upon vector norms, we can define matrix norms which are induced by these vector norms. So I can, for example, I am going to define, and it will of course need a proof, all right, but I am going to define as a candidature that the pth norm A of P, which is induced based upon the pth vector norm, as supremum of A of x, length of A of x of P, no, A over the length of x, P over the length of the x vector for all x not equal to 0. So A is a m cross n matrix, x is an n cross 1 vector from Rn, Ax becomes a vector which is m cross 1. So when I say Ax of P, this is a vector norm from Rm to R plus. And when I say divided by length of x of P, then since x comes from Rn, this is a vector norm from Rn to R plus. So therefore, this is a different norm. This is a different norm. Though the notation looks same, the length of the vectors in one case is Rn, and another case it is Rn. And if you recall what was x of P, it is the pth root of x1 to the power p plus x2 to the power p and so on up to xn to the power of p whole to the pth positive root of this. So this is what is our this is what is our vector norm. Now I am defining this norm, pth norm of this. For example, let me for the sake of discussion take for example second norm. Then I am saying that it is the supremum of what is the f of x. F of x here is this divided by this, where all x are not equal to 0, because division by 0 problem we want to avoid, 0 by 0 problem we want to avoid. Now the first question that comes to your mind is, can I replace supremum, can I replace this supremum by maximum? That is the question that comes to my mind. Now let's look at it carefully. Okay, let me revert back to the generic notation. A of p, I have defined it as this divided by this divided by the length of x, which I can also write as supremum x not equal to 0 ax divided by x divided by length of x and then whole of this of p. Why? Because why can I write like this? Because this is a scalar and the scalar can be taken inside the scalar can be taken inside. Recall this property. Because of this property, if it is outside also I can take it inside, and I am taking right now this scalar to be equal to this. This is the scalar that I am taking, alpha I am taking this. So this is what I have done. It was outside, I moved it inside. But then what is but then what is x divided by length of x of p? This is a unit vector, is it not? Its length is one unit vector in p norm, p vector norm. This is a unit vector in p vector norm. For example, if it was a second norm, then you are saying like x1 square plus x2 square plus xn square is equal to 1. So it's a unit vector in the pth norm. So I can therefore write now my alternate definition as, and supremum always exists, remember that, right? So in terms of supremum I can always write, I will now write this as, look at all vectors of length 1 and then look at the supremum of a of x of p. So now I have used this property that this is a unit length vector. Because this is a unit length vector, x not equal to this and this is a unit length vector, together gives me a constraint that I am looking at all unit length vectors and then taking supremum over a of x of with the vector norm of p. Now the question now I can actually pose to you again this question: can I replace supremum by maximum? And the answer is yes. Why? First of all, set of look at set of all x such that x of p is equal to, I'm sorry, such that the pth norm of the vector is 1. So question is this a compact set? Yes, it is closed. We have, it's very clearly it is closed, and very clearly it is bounded. We have seen this earlier also. It only consists of boundary points. There is no interior point, but yes, it is closed and bounded. We have answered this earlier itself. And what about this function a of x? Is this a continuous? If this is written as f of x, is this a continuous function? Is it a continuous function? The answer is yes. So because this is a vector norm, and vector norm I have already shown to you that it is in the earlier class that it is a continuous function. So therefore what it means is that in this definition, this function is continuous and the set is compact. So by Weierstrass theorem, there exists an x star such that length of x star in the pth norm is 1 and it achieves the maximum. So therefore this you have an x star which will have which will achieve this, which is equal to a x star of p, where length of x star is equal to length of x star is 1. So uh, we have actually shown that now because of Weierstrass theorem we can define pth norm as max. We can replace it by this. The advantage now is that you can say that there is an x star. That's the whole important thing in a x star, such that this is equal to 1 and a of p is equal to a of p, which is equal to a of x of star, is equal to this supremum or maximum of of this is what we are able to now say. I'll write it here, supremum of the ax of p. This is the main advantage of applying Weierstrass theorem. Now since now we need to check, to say that it is norm, we need to check the properties 1, 2 and 3 which the norms require. So first is that ax star x star exists and x star is of length p. X star exists and x star is of the is of the is of the length p. Then ax star I mean x star is of the length 1. Then ax star of p will be greater than 0 if a is not equal to 0 matrix. Is it not? Because see, if A is a non-zero matrix, then you can always find some unit length vector. For example, let's say 1, minus 2, 3, minus minus 3, and let's say 5 in a two-dimensional case. Then I can take, for example, 1, 0 as a vector and sample the first column out and then look at its length. And what is this length? This is under root of 4, which is 2, which is greater than 0. So therefore if the A matrix is not 0, when you at least with some unit length vector, A of x of p will be greater than 0. And since you are looking at max, so therefore with x star it is at the maximum, so the maximum will be always greater than 0. And what happens if A is a 0 matrix? If A is a 0 matrix, whatever you multiply, it will turn out to be 0. So therefore the first property is, as is usually expected, very easily uh, very easily satisfied. Now if you scale this matrix by, let's come to the third property. If you scale this matrix by whole of the matrix by alpha, then actually this alpha being a constant, your problem supreme or let me direct, I can now use maximum itself. Maximum x of p equal to 1, such that alpha of a of, this is what is the, this is how we will be defining this this pth norm of alpha a. But alpha being a constant, I can take it outside. I can instead write it like this, but then this becomes equal to this becomes equal to this. So therefore this property is also easily verified. So then the trick is only in checking the triangular inequality. This is the only thing that that is a bit more challenging always. How to check this triangular inequality. Inequality. So let's do it. It's not a very big thing. Because of the thanks to Weierstrass theorem, we know that there is equal to there exists some unit length vector x star such that this is such that the max problem is satisfied by max problem. What is our max problem? The max problem is length of all x equal to 1, maximize a of x, and x star is its solution. So the max is obtained at this x star, and so you get pth norm as by our definition. This function becomes equal to this, but then this is same as ax star plus bx star pth norm of this vector sum. But these are two vectors of length m cross n. So m cross 1 and m cross 1 which we are added. So triangular inequality applies on them. So triangular inequality applies on them. So therefore you can replace this by less than or equal to length of ax star plus length of bx star. Now what is, see, x star is a unit length vector. So if I look at this is always less than or equal to max of all unit length vectors, all unit length vectors. This is one candidate solution in the feasible space of unit length vectors. This x star is a unit length vector. This is just one feasible solution in this all possible length of unit length vectors. So therefore the pth norm of it is less than or equal to the max of the max achieved here, which is nothing but the pth norm of a. So by similar argument, bx star of length is less than or equal to the pth norm of b. For maximizing it, some other vector may do it or x star may do it. If some other vector does it, this is possible that it is strictly less than, otherwise it is equal. So therefore what happens here now, this becomes less than or equal to length of a, plus this becomes equal to less of length of p. So we have derived the triangular inequality as well, and hence this is a vector norm. For more details I refer you to Golub and Van Loon matrix computations chapter 2. Let's stop this.